Good morning, good afternoon, and good evening. My name is Michelle Loy. I'm with the Financial Management Association International, and I'm very glad to welcome you here today to today's seminar in partnership with the Finance, Economics, and Banking Research Network with Dr. Gordon Phillips. Dr. Phillips is a very good friend of the association. He also happens to be program chair of our upcoming meeting in Taiwan, and of course, a guru in AI and LLMs. So we are very pleased to have him today. With that, I'm going to pass this over to Cesario. Cesario, do you have some opening remarks?
Yeah, just some few words. First of all, to thank Professor Phillips too. It was difficult. It was not easy to find a date regarding his busy agenda, but finally we managed to do it. So once again, thank you very much for being with us today and on behalf of FEBRN and all the attendees. And also to my good friend and colleague, Professor Valerio Poti, which will moderate the seminar today. So without further ado, I pass it to you, Valerio.
Thank you, my friend Cesario, for the opportunity to moderate this seminar and to introduce Professor Phillips as well for being the driving force, really the driving force in organizing this wonderful seminar series. I know that a lot of people contribute to it, but you are the driving force, and many thanks for that. So Professor Phillips is the Lawrence F. Whittemore Professor of Business Administration and Professor of Finance at Tuck School of Business at Dartmouth College. He has a distinguished track record of impactful and, in fact, groundbreaking contributions in financial economics. He brings together expertise from and interest in several disciplines and branches of economics and finance, including industrial organization, M&A, corporate valuation, private equity, venture capital, and also on the methodological front in natural language processing and artificial intelligence and applications thereof to economics and finance. Phillips' recent research has been published in some of the most prestigious scientific journals in economics and finance, such as the Journal of Political Economy, the Journal of Finance, the Review of Economic Studies, and the Review of Financial Studies. And he has been the president of the Midwest Finance Association. One aspect that stands out about Professor Phillips' track record and scientific profile is its eclectic and wide-ranging nature. It resembles as closely as it can get in modern times, perhaps, the ideal of the scientist who, like the Renaissance man, has a multitude of interests. On a personal note, in part, but only in part, somewhat facetiously, if I may, I must say that Professor Phillips poses a bit of a problem to me and people like me. I belong to a class of finance guys who pride themselves on being eclectic and not overly specialized. So when we see the CV of someone who has published more than us, we say, well, but the guy is overly specialized, whereas we are eclectic, Renaissance man-like. You see then, Gordon, why you represent a bit of a problem for us, because you've been both incredibly productive and eclectic. While staying eclectic, Professor Phillips specializes in private equity, mergers, and the impact of households and firms' financial decisions on firms' strategic decisions. His areas of research include household finance, corporate finance, and closer to the topic of the talk today, computational linguistics and AI and finance. His corporate finance work includes studies of private equity, mergers, and competition. His work in AI and finance includes studies of merger synergies and the scope of firms. In this regard, he has been a pioneer in the use of AI to tackle research problems in economics and finance that require handling less structured data, which actually makes the most of the full power of AI. Today, he will give a talk on using AI large language models in finance and economics. So without any further ado, I hand over the virtual floor to Professor Phillips. And many thanks to him for his availability to address us today. Thank you.
Well, thank you very much. You're very kind, Valerio. And I appreciate the very kind introduction. And thanks to the Financial Management Association and the Finance, Economics, and Banking Research Network for inviting me on this talk, and Cesario for being such a great organizer. So, it's a pleasure to be here. So I'm going to jump right in, and I know we have questions you can ask via the chat and via the online Q&A session, and I'll hopefully have some time for those too. I've decided to do more pictures in this talk and more like understanding the concepts. And I was saying I don't think I have any standard errors at all. But there are, for those researchers who want to see all the standard errors, I'll refer you to the papers. But, the talk is about how to use scalable and natural language processing and really understand, financial questions, economics questions. And I've been working on this a long time. And I actually think I've been very, very lucky in my career because I started working on this before it was popular. And then it became popular. So it's like one of those things which I just got I will attribute a lot of my success to luck and just being in the right place at the right time. So, what we're doing here is trying to understand some basic economics questions and finance questions. How do we think about industries, identify competitors, measure competition? And it was, with that vein, I'm going to start off and give you a bunch of economics questions which can be addressed with textual data and large language models. And some of these that we've addressed, but others are still wide open and still, waiting for the right young scholars to dive right in. And the first one is on product differentiation, reducing competition, innovation and change, new markets, disruption. This is a huge topic, and just work on that a little bit. Supply chains, firm complexity, economies of scope, analysis of patent text to understand innovation. And then, kind of expanded markets. We want to also deal with private firms, international firms, public versus private. These are big questions, and we've just kind of taken off slices of some of these. And so there really is lots of good questions to answer. I always say, okay, so you see people say, well, there's all these papers now. People have used large language models and text, but still it's in the dozens. It's in the dozens where if you look at CompuStat and you look at CRISP, we've got thousands of papers. So it's just starting. I think this is really a burgeoning area. The whole point is to think about a network representation of how firms or even individuals are connected. We started thinking about this, about 10 years ago with my friend and co-author Jerry Hoberg. We're thinking of this as like, if you think of Facebook, we're all connected in different degrees of connectedness. Or on LinkedIn, you say, well, I'm 1 or 2 degrees away, from somebody else, maybe 3 degrees, 4 degrees. And here, you can think of firms the same way. They're all connected. You can think of industries as an artificial construct. It's just a question of who affects me the most, or who is close to me in a product sense. And so with text, we're going to show you how we can measure localized competition and find related firms. And this is important in corporate finance and asset pricing when we answer questions about how firms interact together, which is really very important. Yeah. So, let's start off by large language models. Those really started, and we'll take you through the genesis of that. And that is my talk today. I'm going to show you some earlier work before large language models, but we'll jump right into the large language models. And for those of you, this is probably most people on the call. Maybe you know this information already, but it's just a quick review for everyone. You basically have a bunch of text. I have newspapers here on the left, and then it basically takes this enormous voluminous text, turns it into embeddings, and you can use these embeddings are high dimensional, but still not as high as the text. If you think of the text, if you take all the words in newspapers, you probably have got unique words, maybe, over 50,000, close to 100,000, maybe more, depending on the newspapers you're looking at. And that's too high dimensionality when you try to understand things. And early on, if you have a small set of text, you could just do word overlaps and things like this. But as you get larger and larger sets of text, you have to do what's called vectors. You take the text and you convert it into embeddings. So it takes all these words like the, dog, and cat, and it assigns them to areas, which are, B, C, D, E would be the embedding vectors. And so then it understands how firms are related to each other. That, maybe in fact, king and queen are very related to each other, and they share attributes. And this is important for the understanding of language and for linguistics. So how are language models trained? They're trained via Mad Libs. You can think of this as a masking, where they mask a word, like I'd like to say a few, and then the question is, what fills in that blank? More words about the most important invention. Like you could say a few less words. They're going to be related. Those are the opposite, though. So you'd have to try to understand the concept. You could say scientific words about, again, we try to figure out from the surrounding words what would be the right word there. And then, of course, what it does is it can then predict the word that should be there if you leave it out, or even predict the end of a sentence, called phrase masking. So I'm not referring to science. You could say an invention or even the discovery of science. We could say discovery of, a discovery of tomatoes or whatever it might be. Science and tomatoes are probably not used very often together. But we try to understand this with using lots and lots and lots of training sets, lots of documents. And that's why it's been in, these large language models and the big ones you've heard about have been ingesting huge amounts of text on the internet. And they've actually ingested most of things that are published on the internet. So the question is, what do you do next? But we'll do that. And then you can get a whole bunch of other other words meaning. If not for sneakers, our lives. Maybe our feet would be dirty, cold, and miserable. So you get a lot of ideas here. And so there's lots of words that could fill in these blanks. So it is a probabilistic sense that this would be the word given the context. So let's think of these recent development in large language models. You can see 2014 DocVec. So AI and machine learning have been along a long time. But understanding these large language models really started in the first one in 2014. Then you see 2018 with GPT and BERT with Google. You see Roberta. You see in the end 2020 we have Longformer, we have Luke, we have GPT, and then it was 2022 with ChatGPT, the first version, which is not on this chart. So we know that things have been progressing very fast. So here's again LLMs. Here are the very famous ones: BERT, ChatGPT. But there's many out there. Look, there's Ernie, there's Grover, there's there's different transformer, and then there's even cross-lingual. There's video BERT, a whole bunch of different things. So what you choose to use in your task is going to be context dependent. And that's one of the things when you use a large language model. There are many, many, many things. There's a new one out of China called DeepSeek, which works very fast. But again, they're going to have different amounts of accuracy. You're going to make choices on them. So that's one of the things which you will, if you get into this literature, you don't just have regressions. You have, OLS regressions. You have many different types of regressions, and you can see how many different types of transformer models there are here, language models. Okay, so I'm going to go and tell you about the work that I've been involved in a bit, and this is all papers I've written. And so the early work, which is I call text as data, was pre-LLM work, before LLMs. That was before DocVec. We used 10K text to classify firms into network industries. And we have two papers here, which we've been kind enough to have been cited a fair amount. We make all the data available. One is in the RFS 2010, and the other was 2016 in the JPE. In these papers, we did not use a transformer model. We basically just took the text, and we were essentially getting bag of words type things. We're not, word overlaps, product text, and how much things overlapped. These new papers that we're going to be talking about today are LLMs, large language models. The first one we published was in Journal of Finance in 2025. It doesn't say it in the title, but inside of it is a large language model to understand scope, scale, and concentration, the 21st century firm. So we used a large language model, in this case DocVec, the simplest one, to understand how many products firms produce, where we could even take into account, again, the meanings of each word and its surrounding. Product text in the 10Ks was very well-defined corpus, so it worked very well. Now we're using in new research, we have two papers that analyze patent text to understand innovation. And I'll talk about the first one a bit more. It's called Intellectual Property Protection Lost in Competition, an examination using large language models. We hope it comes out on the third round for those people in academia. Should be hopefully accepted soon at the Journal of Financial Economics. But this one is using what we'll see later, modern BERT. And we'll tell you why we chose that one. It's an extension of BERT. Then we have another paper called New Technology Sectoral Assumptions. In this one, we use Google patent vectors and Google embeddings. And actually, is off the shelf. Google has provided a way to understand the classification of patents. Instead of the typical USPTO classification, it shows the relationships between patents. You can go to Google Patents and download these embeddings, and then you can analyze your patent's exposure to different areas. And we've done that in that paper. And so that's a paper we're presenting. I'm not going to talk as much today. But again, that's using the Google patent embeddings. So it's a large language model. It's an extension of BERT. That is applied, is trained specifically to analyze patents. And so we could have done this ourselves, but Google has done it. So we said, we'll just use off the shelf. Google has published their embeddings. And that's the good news about all this research. You publish the embeddings. It's not the same as ChatGPT because you actually publish the embeddings and then your research is replicable. It's replicable by others. Whereas ChatGPT, we know that it can give different answers for different runs that you do. And then finally, we have a new paper I'll talk about today. It is analyzing web text, internet web pages called private firms, friends or foes of public firms. All these papers are on my website, so I invite you to go look at them if you're so inclined and interested. So let me just tell you the building blocks of natural language processing and LLMs. First, you have to have the text. You have to have the text itself. It is a textual model. So our older analysis studying public firms, and we had 2 million 10K firms in total, current project, we use web pages. We have 18 terabytes of stored web pages from the Internet Archive, Wayback Machine, and we're using a high performance network cluster. So these are data intensive, but you don't need to build a $10 billion data center, and you don't have to pay OpenAI or AWS. You can train this yourself, but you do need a pretty fast computer to do this work. Most universities have them. It's still much cheaper to do it yourself. You can also rent space basically rent space online from a company called Vast.ai. I have no interest in them other than they're very good ways to rent space yourself, much cheaper than AWS, at least for our applications. So there's ways to get these projects done at scale without having necessarily machines in your office. So in this case, though, we extracted the business description. We also did extract the MD&A. So this text was very curated, so it was easy to extract, which is good news. But let me just show you what the product text looks like in the case of Apple for 10Ks. Here is two 10Ks, 10 years apart. And the SIC code or the GICs, they were always the same for Apple over this time period. But look at the products they had differently. They had Power Mac, iMac, iBook. Then they still have those products, but they introduced the iPhone, the iPod. They have iPod Classic, iPod Touch, iTunes, Apple TV. Some of these products like Apple TV are not really there. They turned it into streaming. But we do know the iPhone is still going strong. This was in 2009. If we look here are the words, and so we're going to basically extract these words. There were 874 words in the case of Apple. So this is why it gets more difficult than just using one number, like an SIC code. You've got 874 words, and you've got to think about how to classify this firm using the words and its relationship to other firms. If I go on and look 10 years later, you've got the iPhone. And again, you still have the Mac hardware products, and you see you have iPhone and all the words describing the iPhone. And the App Store is described here. In July 2008, the company launched the App Store that allows the user to browse, search third-party apps through a Mac or Windows-based computer. So you get all these words which describing what they do. So it's very, very detailed. And then you have more words in 2009. You have the music products. They had iTunes, which they don't have anymore, but they have, of course, the streaming service and Apple Music. So they change every year, and that's another feature of the text. We have now 3,574 words. So basically, you read all these words in, and you basically put them into vectors, and you understand the relationship. So I have all the words Apple has used to describe itself. I will get rid of the little words like and for, is, and, the words that are common across too many firms. Try to find unique words that apply to, maybe 5% of firms or less. And those words would be somewhat unique to those firms, but are still used by other firms. But it's not used by all firms. So, they're not common words that might be used by half of the economy. Because if I take half the firms traded, that wouldn't give me any real even sense of a local competition or a local network. So I want unique words. They don't have to be totally unique, but I want somewhat rare words that describe Apple and maybe the other firms that Apple is related to. It could be its firms it competes against. As you know, we know some of those. And we know, again, like, for example, Amazon Music, Spotify, they all compete now against Apple to different degrees. So essentially what we do with that is we create this network, and this is a visual representation where we overlaid the industries from S&P, the big industry S&P groups. But you can see these industries are broad, like information technology. It's super broad, and you wouldn't probably want to use this broad definition of industry to understand a technology firm. I would pick a point in the middle here, and I would find firms around that firm which are related. And then the question is, how close do they have to be a direct competitor? So, again, and then you've got healthcare over here, and then we have the green over here, which is, you can see we've got financials. So you've got all these different areas, and some industries really span, like energy. You can see it spans many firms in the economy. So again, probably if you're a solar firm, probably, et cetera. But what we can do is now we can actually get a relationship between these dots. Each dot is a firm, and I can talk about the distance between firms. So this is like a geographical spatial representation. So any two firms in this network will have a distance between themselves, and this will be for 1 year, like 2006. we'd have it for every year. We have it all the way through 2023, all the way starting in about 1980 when we really started using the internet. So you can see a huge amount of data here to construct these relationships, but then we basically reduce the dimensionality down to understanding the relatedness between two firms. This data is all available. So I want to point your attention down here to the firm scope data. These were with embeddings, doc-to-vec embeddings, so it is in a large language model. This is the 2015 Journal of Finance paper. All the data is there, and it really talks about the scope of each firm, the number of product markets a firm operates in. And so we have a database with all that data. And you can see, again, the other data we've done over time we put here, but we're putting all the data online, and we even put some programs there, online for people to use to see how we calculated all this information. It's all there from 1989 through 2023. So we went back in time and really filled it in. Now I'm going to talk about the paper now. Those are the historical papers which we published. I'm going to talk about this new paper, which is R&R at the Journal of Financial Economics. It's called Intellectual Property Protection Lost in Competition, an Examination Using Large Language Models. A lot of words there. But the key thing we wanted to get across, we're discovering intellectual property. We're studying intellectual property. We're going to look at a case where it was lost, and then what happened to competition after we lose protection of intellectual property. And then we're going to use large language models to process the patent text. So the title tells you everything about the paper. And then you go in and see what we've done. The wrong way. Here is the motivation. Maybe this is somewhat obvious too. Innovation is very, very important. I think everybody agrees, so I don't have to spend a long time here. But one point I wanted to say is there's a debate in economics. That's the last point. Bodrin and Levine have a 2013 Journal of Economic Perspectives paper. It's called The Case Against Patents. Reviews previous study and concludes patents stifle productivity, growth, and innovation. What we're going to show is that's not the case. Those conclusions are made based on small samples. And we're going to look at a case where we remove patent protection across a broad swath of firms and then see what happens. And we'll see some firms lose and some firms actually gain. But in fact, we'll see that patents in some cases we think are beneficial and help firms promote innovation, as Nordhaus would say, because you don't innovate a lot if you have no protection. It's always a question of degree. So, there's a big debate out there, what should we do with big technology companies? Again, in the case we're going to look at, if IP protection from patents is lost, what happens? Do firms move towards secrecy and trade secrets? Do IP lawsuits, intellectual property lawsuits increase or decrease? And how does IP protection impact competition between large firms and their smaller competitors? So what is the big case we're looking at? And you can Google this case. It's called Alice versus CLS Bank. You can find the actual patent. It was a patent which ended up setting precedent across a broad swath of industries, not just the one it was operating in. This was operating in basically was a financial firm. Alice firm was patented a system for settlement risk on computers. So basically it was the prior courts went back and forth, and the decision came down against Alice and said their patents were no longer valid. So CLS Bank had sued them because actually Alice had sued CLS Bank and said, you're infringing on our patents. The CLS appealed and went to the Supreme Court eventually because it was 5-5 by previous courts. And then the Supreme Court ruled very strongly in favor of CLS Bank and said they were not infringing, and they ruled against Alice, the plaintiff, and which was Alice was suing CLS Bank. So Alice lost, and the patent actually was revoked. And this was business method patents. It was a huge effect subsequently on the U.S. on patenting. Now, one could argue there were some frivolous patents. Okay, that's fine. But there's a lot of patents. One say for small firms having a patent, it's very important for them. And that's what we're going to see because it keeps them in business and it keeps them, you can get venture capital money. There's lots of good things about patents for small firms, for innovative firms. It helps keep the big firms from stepping on the small firms, let's just say, kind of going into their product space. So in this case, we have a data set of 33,000 patent applications, but not all patent applications made prior to Alice have been rejected. So we have about 100,000 that were accepted by the examiners. So what we do in this case, we using these rejected patents, they cover 5,833 distinct CPC groups, 283 classes, 8 CPC sections. It represented about 17% of patents under review at that time. These are rejected patents. 17% of them in subsequent years were rejected, and the examiner said, we're rejecting the patent, and you can actually find this information out. Unlike why papers are rejected, they publish why it was rejected, and they said it was rejected because of the Alice versus CLS bank decision. Okay, fantastic. But there also are 642,000 pre-existing patents belonging to public firms in these CPC groups. And the question we say, would they be rejected if examined post-Alice? They're still on the books. Just like a publication that uses an incorrect method, it doesn't disappear from the journals. Hopefully people don't use it anymore, but some people might still. So you take these 642,000 existing patents, they're still on the books unless they get overturned by a court subsequently, and the court is not going to examine all 642. So essentially, if Valerio, for example, has a patent and I don't, but I think Valerio's patent is not any good, I could enter his product space, and with a new product that would infringe on his existing products, and I would say, well, sue me, Valerio. Essentially what I'm doing, if you think your patent is still good, and Valerio would have to say, oh, should I sue Phillips for patent infringement? And if indeed Valerio was successful, then I would have to pay damages to him. But otherwise, Valerio's patent could be overturned itself. So in this, it's kind of an unusual case. The patent is not overturned unless Valerio decides to sue me. So his patent is not examined unless he requests it. So a lot of these patents may not be good anymore. They may be vacuous patents, which means people will enter the product space even though there is a patent. And so, but see, this is a hidden exposure. So this is why a large language model is good. We build an AI patent examiner to examine existing patents that Valerio and others have in our little example here, and see if the patents would be overturned if re-examined. It would be a probabilistic assessment. And if that probability is high, we would expect there'll be more entry in Valerio's product space. So that's essentially what the paper is trying to do, to understand hidden exposure. Okay, so what we do is we take the rejected patents and we train a model. So we use modern BERT. Now you could say, why don't I just use ChatGPT off the shelf? It's not as precise. It would not give me accurate predictions. So I train a model. I start with the base embeddings, and then I train it on my data on these 33,000 rejected patents. And then once I train it on a subset of these patents, and I'll tell you what we do. Once I train it, then I go look at the 642,000. Once I have a model, which is a specialized large language model to examine patents. We call it an LLM patent examiner. So it's kind of interesting. You can think of this. We don't need to hire a person. We can examine all 642,000 patents and come up with a score. Would this patent hold up under today's Supreme Court ruling? And then you could, if you're an entrant, you could enter that product space, for example. And that's really an interesting question. The LLM is needed given the uncertainty about the viability of the existing 642,000 patents. And clearly, I can't come up with a way to understand if that patent, because not all of them are going to be invalid, because the Supreme Court doesn't say all patents in this area are invalid. It says a subset of them. And so how do you know which subset? If you're a scientist, you could probably figure it out. And that's what we're implicitly saying. The firms can figure it out. They know which patents are no longer valid, so they know which areas they might want to enter. A venture capitalist could figure it out. But we, as an outsider, as an econometrician, cannot. And we want to understand the exposure of firms so we can understand how competition and entry changes when patent law changes. So we predict using LLM that 16% of granted patents over this period would be rejected if re-examined post-Alice. They're still on the books, but we predict they would be rejected. And then we're saying that other firms, if they have scientists, will know if that patent is not as good, so they might enter Valerio's product space. So we're going to then examine with that prediction the ex post changes in patenting performance, that should say R&D, research and development, and competition for firms with differential exposure to Alice. The key is differential exposure to Alice. And we do find differential effects for large and small firms. So I'll tell you what those are at the end of a few more slides later. So what do? Why is this an LLM application? Well, because it's uncertain, and we have 642,000 patents to examine. So we train it, though. We start with the modern BERT deep learning. It's a deep learning model, but you fine tune it. It was released in 2024, like last year, to classify the likelihood of granted patents being invalid. So modern BERT extends BERT to handle long text and does a whole bunch of other improvements. You can Google modern BERT. So my first pointer to people is don't use BERT anymore. It's the grandfather of all these models. There's now a better one. It's quicker, more accurate. It's called modern BERT, but you still have to train it with your own data. So then we train it, and we train it with these rejected patents, so it becomes more precise than just the untrained version. So here's the idea. You know what happens with, what can it do? Here's a simple example. These fall two sentences on the slide. They mean the same thing, but they have no common words. Symptoms of influenza include fever and nasal congestion. A stuffy nose and elevated temperature are signs you may have the flu. You look at these, modern BERT finds a 98% similarity between these sentences using a TF-IDF model that filters stop words such as, that should say a and, like stop words that like commas and periods and a's and clauses. The sentences have a similarity score of 0 because there's no words that overlap, but we know the meanings. And we're, if you're an English speaker, and what's good, they can do this in Spanish. We can do this in Dutch. We can do this in German now. We can do it in Chinese. All these are there for different languages. So we know the meanings of things. So we show statistically modern BERT outperforms BERT, bag of words, TF-IDF, and word embedding models. And it requires pre-training on existing corpora. For comparison, we also use SciBERT, which is pre-trained for scientific classifications, and it still does better than SciBERT. So this is modern BERT. So you can look these up later, but here's what we do. We take the USPTO, we take the full patent text for these patents. We have 33,000 rejected. And what we do is we train the model using 23,000, and then we take 10,000, or about a third of the sample, and it's a hold-up sample. It's a holdout sample. So we can evaluate how good the model is on patents that we didn't use to train our model. And again, these patent texts, you can have up to 8,000 words in this modern BERT, 8,000 tokens. So it's really long in each one of these patents. We have a control set of negatives using ones that were accepted. So a negative in quotes, because these are accepted, as we're training a model, based on the granularity of patents as CPC section, class, subclass, group, main group. Then we can assess the goodness of fit of the modern BERT with a holdout sample of 10,000 rejected patents. We know they're rejected, and we take ones that are accepted, and we say, how well does the model do? It's like an R-squared for LLMs. So we'll show you what we do. We're going to have several statistics, but we're going to assess the testing stage after training. We have the 10,000 positives, randomly selected. We compare it to 20,000 negatives those are the ones accepted now, that we say negatives, that are randomly selected from the granted patent pool based on the CPC distribution of the whole sample from the overall CPC matching 642,000 patents. To assess the goodness of fit, we produce goodness of fit statistics compared to BERT for TF-IDF and word-to-vec. And TF-IDF to word-to-vec, we use machine learning algorithms using logistic regression, decision tree, and random forest. This paper was a lot of work, but I think it's worth it. So we evaluate it. We do precision, recall, F1 score, and accuracy. You can see what these are. And these are ways people assess the accuracy or efficacy of a machine learning model. And what's good is you do it with holdout samples. So these are not involved in the training. So you have an out-of-sample test for how good your model is. Why do you need an out-of-sample test? That's important, I think. ChatGPT doesn't do this for you. The benefit is you can see out of the sample in which you trained it, would it work elsewhere? Would it work on other patents that were not involved? So it's the problem with these large language models is they fit so accurately within sample. It doesn't mean it works out of sample. So you've got to have a holdout sample in a training set. Okay, so these are the statistics. Look how we did. And these are different. We take all the ones that were rejected and compare them to all the ones that were accepted. And we say, this is ones we know what happened. And then you can see that we don't get 100%. You can think of these like an R-squared. What fraction of patents would we predict accurately that are, you can see the accuracy gets up to about 80% with modern BERT. which is pretty good. That means of the ones that were rejected, we have an 80% accuracy for predicting rejections, and of course, 80% accuracy for predicting the ones that were accepted. So it's not 100%. If we had a crystal ball, we'd have 100%. This is pretty good. I would say as machine learning goes, you want about a 70% or higher accuracy rate. You think of this like an R-squared. It's good. You just have to go out there and try different applications. But you can see other models. So we compare it against, you can see the other models here. That we have 10 other models we compare it against. Longformer, fine-tune, Scibert, Roberta, TF-IDF plus logistic regression. So TF-IDF and WordTivex just cluster things. Then you still have to employ a prediction, a yes, no, or a decision tree or a random forest. You may have seen those in other machine learning papers. But the LLM, which is the top, the transformer model does the best. You can see the accuracy statistics get up there, get pretty high. Whereas some of the others are, if it was random, you would expect a 33% accuracy. So that's what you're expecting. There's one, for some strange reason, does worse than random. So maybe statistically that was going to happen. It's only 26% F1 score. So you'd expect a 33% if it was if you just were randomly flipping a coin. So they all add some value. The modern BERT does the best, and that's the one we use in this paper. And that's a 2024 LLM. So it does better than the earlier ones. So part of the problem with this, or one of the challenges with this literature is you always have to be up on the latest bells and whistles. And they sometimes add value, sometimes they don't. But again, we examine the set of patents of the 642,000. Once we build the model, we examine all the historical patents on the books. And then we look, and these examined patents, we say, of these, we say that a certain fraction, they represent 16% of the total granted patents, so it's a big area. And we use the modern BERT, we find that 17% of the 16% would be rejected if re-examined today according to our model. They have a high predicted likelihood of invalidation if those patents are challenged in a court. So again, if you were holding one of those patents and you had a high score, you probably don't want to challenge, because if you have patent revenues and your patent gets overturned, then everyone knows your patent is not valid anymore. Like that's the emperor who basically says, no, the emperor has no clothes. So you basically want to keep your patents and maybe somebody still pays you for them out of the fear of a lawsuit. Okay, so here's some sample patents with high scores. You can see Qualcomm has some, Walt Disney has some, Oracle has some. And one of the issues we faced, and there are huge values here, some of these are billion-dollar patents. And here's some small firms with patents. You see the numbers here. They still have a high fraction, we call it a treatment value, because a lot of their patents are very valuable at risk. So again, the real question is, where does the venture capitalist enter? Do they enter Qualcomm space, Oracle space, or do they enter down here in Blucora, Extreme Networks, Affymetrix product space? So what we do is we find, and again, I'm not putting any standard errors here, I'm just going to tell you the conclusions. Basically, without the IP protection, small firms basically suffer because they're less able to protect their market segment. So if you're small, the venture capitalist, other firms, and even large firms will enter your product space. If you're large, actually large firms benefit from market-wide weakening of IP protection because they face less direct threats by small, low-share firms, and they could basically reinvent their technology by hiring some of their key employees away. So in the end, the conclusion is there are costs and benefits of IP protection. The cost of decreased IP protection is increased competition for small firms, but strengthening of big tech firms who have other methods of protecting their market share. So it's the small firms who really need the patents. So it's when people say the case against patents, I would disagree. I think the patents are actually hurt bigger firms because small firms can use the patent to challenge the big firm. The benefit of decreased, well, it increases small firm competition, and we have decreased lawsuits because no one's going to sue. Patent trolls are basically lawyers who buy the right to sue on the behest of small firms. They're not all bad, because you think it's like hiring a gunslinger to protect your market share. So I'm going to tell you the new work now. I know I've got about 20 minutes, maybe about 15 minutes left. And this is, I'm going to go over it pretty quickly. We're doing new work now on web pages. We're going to use websites to expand the TNIC. So now we've used the public 10Ks, we've used the patent text, and we said, well, what's the big source of uncertainty? We're going to use websites to expand this our previous network industry classification to include private firms. So our previous work had 5,000 public firms. We're going to go to about 800,000 public and private firms. We call this WTNIC, Web-Based Text Network Industry Classification. And the size of an industry classification is very large. So this is why we need a large language model to reduce the dimensionality, because now we have websites with all their text. And you can see 800,000 websites we've got for over 20 years, because we've got 24 years of data. And that's basically 7.5 trillion network edges to estimate. A network edge is just a relationship between two firms over 2 decades. So we need to reduce the dimensionality, so we have to use embeddings. And so we've got a team which did this. I'm going to call out the whole team members here, which started this research called the WTNIC. It was funded by NSF, which was great. And we had comp sci researchers. The business school professors, or the ones that are economists, are wearing ties. All the others are comp sci people, computer science people, no ties. So you can see who they are. You can see we've got a whole bunch of people. We had 3 institutions. We used about 10 research assistants over 5 years to do this. So we took the web pages, and we'll tell you where we get them and all these things. We get the web pages from, I can tell you now, from the Internet Wayback Machine, and that is the Internet Archive. Over many websites, you see like 7 distinct sections: employment, social media, ESG, blogs, press release, financials, and specific information about the company's products. We want to focus on bullet point 7. 1 to 6, you might be interested: social media, ESG. We weren't in our test, but you can extract it from the web page, and they do put a lot of information there. Okay, so what are we doing here? Early, we had industries where, SIC and NAICS or GICS. We had our TNIC, which is our work earlier on public firms, the 10K. Now we're doing the WTNIC, public and private. We still have the same task here. You can see across here, you start with the website. You have to get the text. You have to get copies of the website. You purge tags. We represent sites as 300 dimensional vectors. So with 300 dimensions, remember now we've got again, almost 1 million firms with 20 years of data. So the number of words is huge. So we have to reduce the dimensionality. We do a cosine similarity again, and we get a product similarity network. But you do a cosine similarity with vectors. It's not with the actual words themselves. And so this has still similar conceptually. We're just going to use large language model here. I'm going to start with a simple one, Doc2Vec. We're going to try a few others as well. But here's an example. Tesla website. We all know Tesla, better or for worse. They have all these different models of products, and their website is super clean. We can grab the product text from the Model S, the Model X, the Model Y, the solar panels, super clean. Every link on the page has clear content. Here's Starbucks. Well, not as clean. They do talk about coffee, but a little bit down here, our coffees. We can grab the our About Us section. We're going to ignore the careers, the social impact, business partners, ordering. So ESG and being a good citizen is also on the website. So here's our solution. We're going to basically use representation learning. You can see Doc2Vec up here, Roberta, LDA. And then we have link prediction, which is those relationships between firms. And then we evaluate it. Profit prediction, NAICS, analyst peers. The problem wasn't the power of the NLP. The issue was webmasters systematically post content not about products. So we have to filter it out. So it's a filtering task. I'm not going to go through what we do on the filtering task. You can find that, but we find that, Roberta does pretty well, and Doc2Vec does the best. It's surprisingly, Doc2Vec is basically does take into account the context. It doesn't have you trained it on your inside the web pages because we have lots of data. It doesn't impose external structures, so I think it works very well. Essentially, 10Ks have worked pretty well, and this is the SEC 10Ks if you train it. But look at the web text. They don't work as well as the SEC text, but we get the LLMs to work pretty darn well. If you ask me, these are R-squared from predicting a firm's profit with the peers' profit. And we think of things like monopoly rates. You don't think there's lots of monopolies out there. Maybe you do. But we want to, and this R says there's about less than 1% monopolies because you have private firms. But here's what this gives us, this method. Here's Apple. Here's the top 10 private firm competitors of Apple. I highlight number 9, Beats by Dre. They're the ones who make, Beats over-the-ear headsets. Apple bought them for $2 billion. They were very related on their web pages. We said they had a similarity score of 0.392. And we see other similarity scores here. They actually are basically people work with Apple. But what was interesting about this firm is they introduced the AirPods, which now would be a $150 billion company if it was standalone. They paid $2 billion for it because everyone's buying those for their kids. They make them in Vietnam for a couple bucks, and they sell them for like, a couple euros, and they sell them for 150 euros in Europe and 150 to 200 in the US. But you can see here's Barrick Gold. So we have now all the private firms, and we have a way to measure how related the private firms are. So now we have a new paper it's on the website called Private Firms, Friends or Foes of Public Firms. And you can see we examine whether private firms produce new products that benefit or complement public firms. That's just a simple question. We can use this database for other things. We did the internet pages we got with the Wayback Machine or the Internet Archive, and that is a historical repository of web pages. The data we have 500,000 plus private firms and 5,000 public firms annually from 2000. We've updated. Now we're going to have it through 2024. And we use, essentially, we call this a WTNIC. We use the WTNIC data I just described, and we use that, again, from the Doc2Vec LLM of market structure from the web pages. Here's what we get. We know the location of these firms as well from the web pages. These are private firms if we take a focal public firm. So we can see what happens to public firms if private firms are shocked. And we look at two types of exogenous shocks. We admit the focal firm state. We can the average R&D tax credit of the firms around it and the average real estate price change of the private firms of each public firm year. We have hundreds of thousands of private firms. We have high power. So now we can see how public firms are impacted by private firms. And then here's a hypothesis we test in the paper. We say acquisitions by public firms of private firms will increase after private firm innovation shocks. And the idea is that private firms develop things, public firms will buy them. And hypothesis 1B, quite related, sales and profits and organic investment of public firms will increase as private firms develop more complementary products. So this would be firms like Agalato we saw for Apple. They produce complementary hardware, all the extra stuff for the new iPhones. General Dynamics nearest private firm peer provides flight simulation services to train pilots. These relationships benefit both parties through product synergies. Now, Apple may buy, just like they bought Beats by Dre, they may buy a Agalato, or they may be separate. But Apple does benefit from having an ecosystem around it. But then we look at real estate liquidity shocks, because here we have, these are developing new products. Real estate relaxes financial constraints that are favorable to private firms if you get a positive real estate shock. And we find in that case, there's a negative impact on public firms. Like Boeing's nearest peer, Boomsonic, produces competing aircraft. CVS closest peer, private firm Maxor, is a competing pharmacy. These relationships are substitutive, not complementary, and we can actually document that. And so here's how we do the innovation shocks, the non-innovation shocks. We think of these as exogenous because we're going to have, real estate and how it affects private firms competing against Apple, or, again, the R&D tax credit. And the shock aggregation method, we exclude firms in the same state for exogeneity. But here's the results, and I'm just going to no tables, no standard errors. Private firm innovation shocks need complementarities for public peers. Private firms increase investments, R&D, and acquisitions. Public firms, they experience higher sales growth. That's good. When the private firms benefit, because everybody's doing more products, and so this is going to benefit even the public firms. It's complementaries. Fluidity and secrecy increase. If I look at non-innovation focused shocks, real estate shocks, they have the opposite substitute effects. Public firms decrease investments in patents. Private firms benefit because they have more access to capital. So they start displacing public firms. So here's, again, if I look at innovation incentives, here's what we find. Large firms, more acquisitions, moderate increase in R&D, higher ROA. Small firms also increase R&D. They don't do acquisitions. Some sales and asset growth. They have a decline in ROA, again, because the large firms are here, and these guys are investing, I think, a lot. When private firms shock with liquidity, opposite results indicate substitution effects. So this is, and then we have some competition results as well. If you look at high competition firms, we see a stronger increase in acquisitions. They try to buy their competitors. When they have a lot of competition, they also do more R&D and patenting. When they buy their competitors, they're buying their private firms. We see steeper gains in sales and asset growth, a greater decrease in competition. over time. They bear the brunt of substitution effects from non-innovation shocks. But low competition, if you're in like a very protected market, you focus on maintaining your barriers to entry, you have a moderate increase in innovation, you're more resilient to innovation shocks. They appear to enjoy the quiet life, but take advantage of the rents. So this is the competition results in the paper. And that's it. The paper will have, lots of tables demonstrating these things and, describing the methods, but I haven't shown you the, the coefficients. You can look at the economic size of them and how significant they are on your own. The innovation shocks, if you want to remember what the paper is about, private firms develop complementary products, large firms acquire private firms to commercialize the innovation. It's consistent with innovation outsourcing, and I have an article that has a theory paper with some initial evidence. This is much more in-depth evidence here. Non-innovation shocks, private firms become stronger competitors. Increased liquidity enables private firms to challenge public firms. And private firms move products closer to becoming substitutes. So the data for all this, remember the data. If you remember anything else, you got the paper. The new data is WTNIC. We'll put it on the website very shortly. It covers 5,000 public, and it expands it to 500,000 plus private firms using corporate websites. So it's a new source of data. Separating product vocabulary from other types of website vocabulary is hard. We use LLM embeddings to maximize the signal and topic models to purge non-product content. WTNIC performs as good for private firms as baseline TNIC does for public firms. So this is going to be a great resource, and we'll make it available. It's for free. All the data will be there, and you could link it up with patent data. You could link it up with M&A data. We'll do some of those links ourselves. But why do all this? Why do all this work on web pages? I think here's the big point. There are major concerns about declining competition, innovation in the United States. Hard to find data on early stage firms. That's a practical one. But the new economy involves firms with multidimensional products. We can measure this with text. And we can also identify frictions like changes in IP rules or provide right incentives, for policymakers, eventually the right policy choices. Well, this is a bit of a claim. You can little bit extra for the next 100 years. I don't know, for the next 5 years at least. Let's put it at 5. The counterfactual without, is weakly established. If you don't have this detailed data, you have a policy of trial and error, with again, politicians making policies that might hurt the economy. One example is if you tighten too much down on mergers, then you're not going to get venture capital financed firms. So because venture capitalists need to exit, and most of the exits of these innovative firms, in many cases, are in fact a sale to a larger firm which commercializes it. So it's like an early stage incubator. So if you have policy, especially I think in Europe and even in the United States recently, where they're trying to block M&A of small firms, that could have an adverse effect on innovation. Even though they have good intentions, they want to protect the consumer, you might actually hurt the consumer, and that's what we've been showing. The LLM textual analysis and research has the potential to pick out these complex interactions, and we hope the policymakers listen to some of the conclusions. So here's the conclusions about AI, LLMs, and finance and economics. We began this with just textual measures without LLMs. New methods, the first one we've done is in DocVec in 2025, but now we're doing a modern BERT, kind of the most modern machine learning transformer models. And then we're going to expand to private firms. And we're initially using DocVec. I could imagine us using modern BERT or something equivalent, analyzing firm web pages over 24 years with new transformer models that just completed. We think there's many applications, economic tests. We have more data, more ways to analyze it. So we think it's productive. So with that, Valerio, and I went I know you told me 50 minutes, so I went three minutes over, but it's been my pleasure, and I look forward to some questions now.
Gordon, actually, many thanks. It has been our pleasure to listen to this wonderful presentation. I mean, the comments that are coming are sort of all about that tenor. I mean, so the presentation has been wonderful. So, and there are so many interesting questions. So what I propose to do is that I summarize sort of the kind of 3-4 blocks of questions that we are getting. Okay, so I do my best to summarize, right, to condense in 3-4 blocks. And then, I mean, then you can choose whichever you want to answer. So then again, many thanks for this wonderful presentation. Yeah. So the questions that are coming, I think, can be grouped as follows. So the first type of questions is on how do we distinguish closeness of firms, right? Or different types of firms? For example, how do we distinguish closeness of competitors from closeness of firms along a supply chain?
Sure.
For example, someone was saying, you know, words like iPhone can only be found in the Apple 10K. Why is that useful to establish closeness to firms that don't do the iPhone?
Well, the iPhone itself would it is possible that other firms could say, I sell, you know, for example, software that works with the iPhone, and they have to put a trademark symbol on it, trademark of Apple. So it is, even though it's just used by Apple, that would be a direct link. You could in fact, you know, when they're selling, you know, cases for the iPhone. Now, a question about a supplier versus a competitor is a good one. We actually, or someone has a very good question. We've done some work distinguishing the two, and there's a paper on vertical integration we have. And so we have a method. One method is we take the Bureau of Economic Analysis, which has input-output table, and then we can look the words in the input-output table and map firms into the input-output table. So clearly, if they list themselves, if they say themselves in their web page or their 10K, they directly say I'm supplying stuff to Apple, then we know that they're a supplier. Well, they may not say it, right, if they're not a supplier. So we can look at the similarity of firms that identify as suppliers to the supplier itself. So there's a whole bunch of different ways to do that, and we've done some of that. So the good news is closeness doesn't have to just use the word iPhone. It could be used telecommunications. It could use App Store. It could use I'm selling things on the App Store. There's lots of words in that Apple 10K. So you don't just need one word. What you end up having is they have to have, in our case for their initial paper, they had to have 23% common words out of all the words that they use. That, you know, these are words they share. You can think of the words overlap. So there's lots of words that are still distinct. You know, we've gotten rid of the prepositions, the adverbs, the has, the thus. There's still words that are there. And we have examples in the paper of words that might be distinguishing. We know you can actually see the words that Apple uses that are other firms uses. And there's going to be a lot of them. It's not just one word. So you're not looking for one exact word. All we need is 23% of your words are shared with Apple, and then you're a competitor. So it's, why do we use that exact figure? It depends how many industries you want, how close you want that circle to be around that diagram. So the closeness is the word overlap. That is that diagram we brought up. If I go back to it, I'll show it to you again. Show everybody that diagram, which I think is one of the cooler diagrams, if I have to say it myself, that we have. So you'd say Apple, let's say Apple's right in the middle of information technology. The distance between them would be the number of words they share. So actually there's a score all the way out there for even aluminum firm. It would be probably close to zero because they're so far away and there's nothing they share. But, you know, because we've gotten rid of the common boilerplate words, we stripped those out. So again, 23% was in that thing. In the embeddings analogy, once you do embeddings, they would have to have high scores on certain embeddings that are common to Apple. So again, it would be a scoring-based method for like how many words you share. And you actually do what's called a dot product. I don't want to go into the details, but you multiply two vectors, and then this is why you need these graphics with NVIDIA, because what NVIDIA is selling is a GPU that is really good at matrix inversion without going into the math, because you have all these vectors, you're multiplying word vectors, which are long, by each other. You have to, to get relationships. Even in OLS, we do a matrix inversion. So that is the thing that the graphics chips do so well.
Right. Thank you very much. Thank you very much, Gordon. I mean, actually, there is a possibly relevant question that just came in, actually. So wondering how misclassification of clusters may actually end up biasing the estimate of the relationship, for example, between the Alice risk score, and the firm level outcomes, right? So
sure. I mean, it could be misclassified, but then we look at the results. And that's why, it's 80% accurate. And then the question is, if it's 80% accurate on the out of sample test, we think it's very good. So there's 20% misclassified. Okay, fine. But that doesn't mean that doesn't have a relationship. It just means that for some reason, the patent examiner approved it, even though our model says it rejects, or vice versa. And that's measurement error. And we all have techniques for dealing with that. And we think this is low compared to most economic results. If you think of the
Yeah,
measurement error.
no, that.
And you always have some of that, and maybe you can get a better LLM where you get that accuracy up to we've got it up to 80%. Maybe we can get it up to 85 or 90. Maybe again with DeepSeek or something, there'll be a new LLM that makes it. But we look at the predictions; they all make economic sense. And then we do some validation tests, which we're very excited show that hey, it does predict what we think it should. Lawsuits go down, which might be a good thing. People don't sue. Like if you had one of those patents, Valerio, you wouldn't sue me even if I infringe, because you'd be like, oh, I don't want to lose out. If I get re-examined, I could lose in court.
Yeah. Oh, and actually, many thanks, Gordon. That's really clear, really insightful. And actually, it actually brings us very naturally to the second cluster of questions, which is basically about essentially whether we can use large language models to do identification, econometric identification, right? But basically whether we can use them for causal inference in empirical finance.
Causal inference, you still need a shock. Like we had the Supreme Court decision. So a lot of things, that's exogenous because it was 5-5 in previous one. So that was there. And so in other cases, you still have to worry about identification, but it doesn't mean you can't, you can rule out some things pretty clearly in some cases. Like most of this stuff we're doing with spatial representation, it's a relationship. We don't have to worry about identification here. Two firms are related. Okay, yeah. We don't have to say why they're related. Then we can look at what happens 2 or 3 years later if you're related versus you're not related. And then you say, okay, I'm more likely to buy you. I have a successful merger.
And then you still need a shock. Then you still need an
exogenous. Could have a shock, and but in some sense, I think there's some interesting things that could be established. Like, let's say you and I are related, and then I find two firms are related today, and I look at is there a higher likelihood that the one firm will buy the other firm? Well, I think if we're related, we do similar stuff. The likelihood is there. Now you could look at a change in the merger law. And then a merger law which relaxes the ability to do mergers. Who am I going to buy? Well, I'm going to buy the firm that's related to me now that the cost of the merger has gone down. So that kind of tells you, and this could happen 2 or 3 years after we establish the score. So, and there's, personally, I say if you're becoming more, if you produce products that are close to me because you want to be bought by me, so that might be a strategy too. Venture capitalists talk about that. They produce products that are useful. So, I don't think I worry as much about identification as many people in the identification police. You need a shock, and that's what we have, some exogenous shocks. But you have to these are basic economic forces.
Gordon, actually, many thanks. And actually, that brings me to sort of a kind of stress and insight that you provided that I found was very interesting. The fact that you said that you can use large language models to essentially replicate a particular type of counterfactual. I mean, to replicate the decision of a decision maker, of a standard decision maker. And now I have a question. Would it be a rational decision maker or would it be a standard decision maker? Because
it's the decision maker that's in your model, like a patent examiner.
Yeah.
I don't think any model is going to be able to predict what Trump is going to do. So so if they're crazy, then we can't predict. But if you think of a normal, maybe somebody who has a set of rules and institutions who operates in a certain fashion, and as long as those institutions don't get shocked, then of course you can predict what they may do. It's not 100% right, but I gave you the best example is no one can predict what Trump is going to do or say sometimes. So that the model will never work there. But if you try to predict, the chairman of the Fed, and you you look at the text, you can predict. People actually parse the text of the Fed statements to try to figure out if they're going to cut interest rates. Right, and so they're trying to predict in a very simple, that is a simple linguistics model. You look at the text and there's certain phrases that get included. And then you say, well, the probability of a 0.25% interest hike or a 0.5% interest hike, that the chairman of the Fed is going to do,
I found fascinating the idea that you can sort of essentially kind of replicate what a venture capitalist would do, right, in the face, in the face of the sentence, right, in the face of the Alice, sort of a court case, right, you don't have certain outcomes, you don't observe them, but you can actually replicate what the likely outcomes would be, right?
We try to. That's the point. It's these models. Again, let me actually be quite clear. It's not 100% accurate. It is 80 some percent accurate, but that's very good. As these things go. And so
when you think about it in empirical asset pricing, people do something similar, right? People use vector autoregressions to replicate a marginal investor, right? Which in that case will be an investor endowed with rational expectation. I guess this will be a standard firm, right?
It's a firm that you've used to train the model. We trained it on actual patent examiner decisions in that one case, and so there it's quite clear who are trying to replicate. Now, if there's some crazy patent examiner who just randomly does decisions, then we can't do anything.
Fantastic. Many thanks, Gordon. And then there is the next cluster of questions is about sort of the training process. So whether there is a gold standard in the training process, how do you choose hyperparameters? If there is an ideal way to choose the hyperparameters, how sensitive are your results to that? And I guess my question, one question that I would have related to that is whether sort of what you do, for example, with the modern BERT or with BERT or modern BERT. Is whether you're doing so-called fine-tuning, right?
Yes, we do. Yeah, well, they have already fine-tuned it on like patents in some cases, or Wikipedia. They've already fine-tuned it. They don't want to see the issues. You don't want to train it on, like a Twitter or X, because there's a lot of crazy stuff there. It's like it's not very good. You want to train it on a set of data which you trust in your specific example. Now, you could do it on scientific corpuses, and that's what they do for the Google does. For the Google patent embeddings. In our case, we take modern BERT, and then the paper will have the details about the hyperparameters and all the other good stuff that people are asking about, like how do you train it? We trained it on a set of 20,000 patents. We have very detailed stuff in the paper. Those are the ones rejected, and we have the ones that are accepted. Those we actually include another 20,000 that are accepted, then we increase it 40,000 accepted, 60,000 accepted, and we train the model. And then we see how it changes based on your training sets to make sure it's robust. And then you have a holdout sample where you evaluate how well the model does. And that's where you get the 80% accuracy in the holdout sample. Before you apply it to the 642,000 patents. So that's the one where we don't involve them in the training because they've been accepted. But what we're trying to say is if re-examined today under the current regime, would they be rejected or not?
And I guess there are questions. Sorry.
All those details are in the paper. I refer the interested. We have a technical appendix to the paper that is hopefully detailed enough. If the technical appendix doesn't answer your question, then shoot us an email.
Thanks, Gordon. I guess there are questions also, somewhat related questions that are coming in about sort of precautions that must be taken or could be taken when applying large language models in finance research. For example, a question on whether sort of you should train a local large language model, for reproducibility and sort of keep a record of what your local large language model looked like at the time of doing that.
You can save your embeddings from the final model, and then you can post those so everyone has your embeddings and they can evaluate them, and you have the patent text. The patent text is all publicly available. The good news about the Google embeddings, which we've used in one paper, is they're publicly available already. And then you just take your patents and you run them against it. So it's very replicable to anybody. So the replication is the key to this. So it kind of unveils the black box. But you publish everything on GitHub, and or else publish it on your website. And then people have done this in other contexts. There's a whole bunch of others. There's like Stories LLM. There's people worry about look-ahead bias in some contexts. There's lots of issues to think about. We've thought about those, and we're confident we're okay. But again, all the different parameters you set. How big does your training sample have to be? All these are questions that are fair things to ask. So I do think fine-tuning it is quite important.
I just want to say once again, thank you very much for accepting our invitation. Thank you, Valerio, for moderating the seminar. And to all our attendees, the papers from Professor Phillips are available in his website, and Michelle also put the link in SSRN. They are as well in SSRN in the February Research Paper Series. Thank you very much to allow us to have your paper in our series. So you can...
Grazie mille, Valerio.
Prego. It was an absolute pleasure, Gordon. That was an amazing seminar. Many thanks. Really, really many thanks.
Love it. And this is great. Really, and again, for those in the audience, go consult the text of the papers. We'll post these these slides, I believe. The FMA will post them, and then we'll, I'm always available if you go to the paper and you say, oh, well, this is the one detail is missing. I hope we were comprehensive, but if we're not, just send me an email.
Yep, absolutely. On behalf of the FMA, thanks again, Gordon. For everybody in the audience, yes, I did drop a few links in the chat. I dropped the link to the IP protection paper as well as the vertical integration paper. But of course, if you go to Dr. Phillips's website, you'll find everything there. We will send all of the questions his way. We did get over 20 questions, so a very engaging topic. Thank you so much, Gordon. Join us in October for a seminar with Daryl Duffy. Thank you, everybody.
Thank you, everyone, and hope to see you at a conference, perhaps at the FMA in Asia or the FMA in Vancouver.
Yes,
So thank you.
absolutely.
Many thanks.
Thank you.
Thank you.
Have a great day.
Take care.
Grazie.
Take care.
Cesario. Grazie.
Many thanks. Thank you.